Space is not the silent void we imagine. It crackles with whispers we cannot yet translate, a symphony of strange signals from the clouds of gas drifting between the stars. For decades, our most powerful telescopes have been capturing these cryptic messages, pulses and glows that defy simple explanation. Today, we are diving into 25 of the most perplexing cosmic transmissions, signals from interstellar gas clouds that have left the world's leading astronomers utterly baffled. By the end, you will have toured the very frontier of cosmic mystery, understanding the questions that define modern astronomy. What cosmic event could blast a millisecond burst with the energy of 1,000 suns, and why would another signal repeat with clockwork precision every 16 days? Each unexplained whisper is a piece of a puzzle spanning the entire universe. What do you think it means when the cosmos refuses to stay quiet? The most famous cosmic whisper in history arrived on a quiet Ohio night in August 1977. Astronomer Jerry Amon was reviewing data from the Big Ear radio telescope, a routine scan of the constellation Sagittarius, when he saw a sequence of letters and numbers so extraordinary he circled it in red pen and wrote one word beside it: wow. That printout, with its now iconic code 6EQUJ5, represented a radio burst 76 times louder than the background noise of space, a narrowband signal precisely tuned to the natural frequency of hydrogen. It appeared and vanished in 72 seconds, never to be heard again. For decades, the WOW signal stood as the prime candidate for a message from an alien civilization, a deliberate beacon screaming into the cosmic silence. But a quieter, more natural explanation has slowly gained ground, one that ties this legendary event directly to our tour of interstellar mysteries. What if the WOW signal did not come from a star or a planet, but from a vast, drifting cloud of hydrogen gas? The theory suggests that within certain dense interstellar clouds, a natural process called a maser, which is like a laser but for microwave radio waves, could occur. If conditions were just right, the cloud could act as a cosmic amplifier, taking a faint background signal and boosting it to an incredible intensity for a brief moment before the delicate alignment collapsed. This would explain the signal's power, its precise hydrogen frequency, and most importantly, its heartbreaking transience. A natural maser flare in a gas cloud is a fleeting event, not a repeating broadcast. This idea is compelling because it uses known physics to explain an extraordinary observation, yet it remains deeply controversial. It challenges our deepest hopes by offering a celestial mirage instead of a handshake from the stars. So, the WOW signal's mystery endures not as a choice between natural and artificial, but as a question of cosmic architecture. Did we intercept a 1 in a billion natural amplification event from a silent cloud, or did we truly hear a distant hello? The WOW signal's lonely cry was a puzzle confined to our own galaxy, but in 2007, a discovery would tear open the cosmic map, revealing that the universe itself was screaming. Buried in archival data from the Parkes radio telescope in Australia was a spike of radio energy so powerful, so brief, and so alien that the astronomer who found it, Duncan Lorimer, initially thought it must be an error. It lasted just 5 milliseconds. In that sliver of a second, it released more energy than our sun emits in a month. This was the Lorimer burst, the first recognized fast radio burst, and it did not come from anywhere nearby. The key clue was in its dispersion measure. As a radio signal travels across the cosmos, it plows through the sparse sea of electrons in interstellar and intergalactic space. Higher frequency waves travel a tiny bit faster than lower ones, causing the burst to smear out, arriving as a descending chirp. The immense smear of the Lorimer burst pointed to a journey through an almost unimaginable amount of material. It had come from far, far beyond the Milky Way, from a source billions of light years away. This changed everything. A 5-millisecond event from another galaxy meant the source had to be incredibly small and dense, likely no bigger than a city. Neutron stars, the collapsed cores of dead suns, immediately became prime suspects. Early theories swirled around catastrophic one-time events within a distant galaxy's vast halo of hot gas. Perhaps it was the final death cry of a neutron star collapsing into a black hole, or a colossal flare from a magnetar, a neutron star with a magnetic field trillions of times stronger than Earth. The Lorimer burst was not just a new signal, it was a new class of cosmic phenomenon, a revolutionary shock that proved the universe was filled with these brilliant, mysterious flashes. It forced astronomers to ask a terrifying and thrilling question: what kind of cosmic powerhouse smaller than a planet can outshine an entire galaxy for a single blinding moment? The Lorimer burst's one-off nature made it a ghost impossible to study. Then, in 2012, a new signal broke all the rules. FRB 121102 did not just flash once and vanish. It erupted again and again and again. This was not a cosmic catastrophe, it was a behavior. For the first time, astronomers could point their most powerful telescopes at a precise patch of sky, knowing the signal would likely return. That precision led to a monumental discovery. FRB 121102 was not coming from the serene halo of an old galaxy. It was pinpointed to a tiny, rambunctious dwarf galaxy over 3 billion light-years away, a place crackling with the violent energy of creation. This galaxy is a stellar nursery, a roiling cauldron of turbulent gas and dust where stars are born at a ferocious rate. Within that chaos, the repeating bursts seemed to originate from an extreme environment, a region thick with the plasma of a glowing nebula. This location was a vital clue. It pointed squarely at a specific type of cosmic powerhouse likely born in such a place, a magnetar. Imagine the core of a massive star, recently exploded in a supernova within that star-forming cloud. Its collapsed heart, spinning furiously, is a magnetar, a neutron star with a magnetic field so intense it could erase a credit card from halfway to the moon. Theorists now paint a compelling picture. This young, hyperactive magnetar is not floating in empty space. It is embedded in the remnant cloud from its own birth, a thick soup of charged particles. When the magnetar's crust undergoes a starquake, a sudden, titanic rearrangement of its surface, it unleashes an immense blast of energy. That blast slams into the surrounding plasma cloud, creating a shockwave that energizes the particles and generates the brilliant, repeating radio flashes we detect as fast radio bursts. FRB 121102 became the Rosetta Stone for these phenomena. It proved they could be recurring events tied to specific, violent environments. It transformed the mystery from what could possibly cause a single flash to a new, more focused question. How does the turbulent cradle of a star's birth forge the engine for the universe's most brilliant and persistent radio sirens? The repeating bursts from that distant dwarf galaxy were just the beginning. A quiet revolution was underway in a Canadian valley where a telescope unlike any other was about to rewrite the rules of cosmic whispers. The Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, was not built to hunt for fast radio bursts. Its primary mission was to create a three-dimensional map of the universe's history by detecting the faint radio glow of cosmic hydrogen. To do this, it needed an immense field of view, a vast stationary array of metal mesh cylinders that scans the entire northern sky every single day. This design, by pure accident, made CHIME the most prolific FRB hunter in history. It is not a precision sniper rifle pointed at one target. It is a wide net cast across the entire ocean of the sky, and it began catching brilliant, fleeting fish by the dozens. The statistical revelation was staggering. Before CHIME, FRBs were rare treasures. After CHIME, they became a daily occurrence. The data suggests these brilliant millisecond flashes are not rare cosmic fireworks. They are common, happening thousands of times a day across the entire observable universe. This flood of data did more than just add to a list. It allowed scientists to use the bursts themselves as tools, as cosmic flashlights. When an FRB travels to us, its journey is not through empty space. It passes through the diffuse halos of hot gas that surround galaxies, through the wispy filaments of the cosmic web, and sometimes directly through the turbulent hearts of interstellar gas clouds. Each of these environments leaves a fingerprint on the signal. The electrons in these clouds scatter and delay the radio waves, smearing the burst-sharp pulse into a longer, softer chirp. By carefully measuring this scattering, astronomers can deduce what the signal passed through. A highly scattered burst is like a voice shouting through a thick fog. It tells us that between that distant galaxy and our telescopes lies a significant amount of turbulent, ionized material, perhaps a massive galactic gas cloud we could never see directly. Chiming in transformed the mystery. It moved us from studying individual, exotic events to understanding a population, a natural part of the universe's soundtrack. The question is no longer if we will find more, but what these thousands of daily messengers are revealing about the invisible structures, the vast and silent clouds that fill the spaces between the stars and the galaxies. The sheer number of flashes revealed by Chime began to show patterns, but one signal stood apart by following a rhythm no one expected. FRB 180916.J0158 plus 65 did something extraordinary. It kept a schedule. For approximately 4 days, it would erupt with multiple bursts. Then, for the next 12.35 days, it would fall completely silent. This active and quiet cycle repeated with clockwork precision every 16.35 days. This was not random chaos, it was a cosmic metronome, a clear sign that the environment around the source was changing in a predictable, repeating way. The most compelling explanation paints a dramatic scene of celestial partnership. Imagine a binary star system where two objects are locked in a gravitational dance. One is an incredibly dense, energetic object like a magnetar, a neutron star with a ferocious magnetic field. Its companion is a massive, bloated star, perhaps a blue supergiant, shedding a powerful wind of gas and dust into space. As the magnetar orbits its companion, it plows through this thick circumstellar disk of material during part of its 16-day journey. This dense cloud of gas acts as a natural shutter. When the magnetar is behind this veil, its radio emissions might be absorbed or scattered, effectively turning off the signal from our perspective. Alternatively, the interaction itself could be the trigger. The immense pressure of plowing through the disk could periodically squeeze the magnetar, stressing its crust and sparking the starquakes that produce the burst like clockwork. The 4 days of activity could represent the precise window when the magnetar is either entering or exiting the densest part of this gaseous environment, where conditions are just right for the fireworks to begin. This theory elegantly explains the periodicity by using the orbital mechanics of a binary system and the obscuring power of an interstellar gas cloud. It suggests we are not just seeing a lone powerhouse, but a complex celestial relationship where the signal's very existence is governed by a rhythmic dance through a cosmic fog. Our own galactic backyard holds a monument to past violence on a scale that dwarfs any single star. At the heart of the Milky Way, invisible to our eyes but blazing in radio light, are colossal structures known as the Fermi bubbles. These are twin lobes of superheated gas, each towering 25,000 light-years above and below the galactic plane, a total structure spanning half the visible sky. They are a ghostly imprint, a fossil remnant of a cataclysm that occurred millions of years ago. Within and around these vast radio-emitting bubbles lies an even stranger forest of phenomena, hundreds of magnetized filaments. These are long, thin threads of energetic particles, some stretching over 150 light-years, all aligned almost perfectly with the galaxy's magnetic field like cosmic harp strings. These are not brief signals but persistent, structured emissions from the most immense interstellar gas clouds we can observe. The energy source is almost certainly our galaxy's supermassive black hole, Sagittarius, a star. But its present state is quiet, a sleeping giant. The bubbles and filaments are the evidence of a different era, a time when Sagittarius, a star, was an active monster. The central puzzle is what specific tantrum it threw. Was it a quasar-like outburst, a sudden and gluttonous feast where it consumed a vast cloud of gas, or an entire star cluster, channeling the energy into two opposing jets that inflated these bubbles? Or was it a slower, more prolonged frenzy of smaller meals that built up the structure over millennia? The filaments add a deeper layer of mystery. How do these magnetic structures, thinner than they are long by a factor of over 1,000, form and maintain their incredible coherence for millions of years within such a turbulent environment? It is as if you blew a gigantic soap bubble, and inside it, impossibly straight, glowing wires spontaneously arranged themselves and refused to tangle. One leading theory suggests they are cosmic scars, the aftermath of a massive, one-time outburst that sent a shockwave plowing through the galactic center's tangled magnetic field. As the shockwave expanded, it could have stretched and compressed lines of magnetic force, trapping electrons along them like beads on a wire, causing them to glow in radio waves for eons. The Fermi bubbles and their filaments are a crime scene frozen in time. We see the aftermath, the still glowing remnants of the gas that was heated and shaped. But we are left to piece together the nature of the explosive event, the single bad day for our galaxy that left a pair of radio ghosts towering over us all. While the Fermi bubbles are monuments to past violence, other ghostly structures are on a collision course with our galaxy's future. Drifting silently in the galactic halo are vast, ethereal rivers of gas known as high-velocity clouds. These are not collections of stars but colossal reservoirs of mostly hydrogen, some so large they could contain the material for millions of suns. They move at speeds hundreds of kilometers per second relative to the Milky Way's rotation, and one in particular, the Smith Cloud, is headed straight for us. Discovered by astronomy student Gail Smith in 1963, this cloud is a titan over 11,000 light-years long and 2,500 light-years wide, carrying enough gas to forge 2 million stars like our own. Its trajectory is unmistakable. It is plummeting toward the Milky Way's disk and will crash into the spiral arm we call the Perseus arm in roughly 30 million years. But the mystery is not its destination, it is its origin. Where did this celestial ghost ship come from, and what is it made of? Astronomers detect these clouds through a cosmic fingerprint, the 21-centimeter line. This is a faint but constant radio whisper emitted by neutral hydrogen atoms when the spin of their single electron flips. It is a universal beacon for cold gas. By mapping the subtle shifts in this frequency caused by the cloud's motion, we can trace its path and speed. The Smith Cloud's velocity and path suggest it might be on a boomerang orbit, having been ripped from the outer edges of the Milky Way long ago and now falling back in. Yet its chemical composition tells a more exotic story. The cloud's metallicity, a measure of elements heavier than hydrogen and helium, is the key clue. If it were pure, primordial gas from outside the galaxy, it would be nearly pristine, lacking these heavier elements forged in stellar furnaces. But the Smith Cloud shows signs of pollution. It contains sulfur and oxygen, elements that must have been created inside stars. This points to a dramatic past. Perhaps it is the shredded remnant of a dwarf galaxy that ventured too close to the Milky Way, its stars torn away by tidal forces, leaving only this gaseous corpse behind. Or it could be gas that was originally ejected from our own galaxy's disk by supernova explosions, launched into the halo only to now come crashing back home. When it finally collides, the impact will be a spectacle of creation, not destruction. The immense shockwave will compress trillions of tons of hydrogen, triggering a fireworks display of star formation that will light up that spiral arm for millions of years. The Smith cloud is a herald, a silent, gaseous messenger whose very atoms hold the story of its birth and a preview of our galaxy's ongoing dynamic evolution. A sea of invisible fog hangs at the very heart of our galaxy. It does not glow with starlight, but with something far stranger, a faint, persistent hum of microwaves and gamma rays. This is the galactic center microwave haze, a colossal and puzzling structure first mapped in detail by the Wilkinson microwave anisotropy probe and later by the Planck satellite. Unlike the sharp filaments of the Fermi bubbles, this haze is a diffuse, fog-like glow, a vast bowl of energy centered on Sagittarius, a star, and extending thousands of light years above and below the galactic plane. This whisper is not from hot gas itself, but from what is moving through it. The haze is a textbook example of synchrotron radiation, the light given off when electrons, whipped to nearly the speed of light, spiral around magnetic field lines. The very existence of this haze means the galactic center is permeated by a sea of these high-energy particles, all crashing into the magnetic fields woven through its immense gas clouds. But where did this relentless sea of electrons come from? The debate splits astronomers into two camps, each pointing to a different scale of cosmic violence. The first theory argues for a slow, steady buildup over millions of years. The galactic center is a crowded, ancient place littered with the remnants of dead stars. Could this haze simply be the accumulated exhaust from countless supernovae? Each dying star's shockwave can accelerate particles to fantastic speeds, and over eons, this cosmic pollution could fill the central clouds, creating the diffuse glow we see. It is a plausible, almost mundane explanation. The second theory is far more dramatic. It points to a single, catastrophic event, a recent and powerful outburst from our dormant supermassive black hole. Imagine Sagittarius, a star waking from its slumber, perhaps consuming a large gas cloud, and in a fit of activity, blasting out jets of high-energy particles. Those particles would flood into the surrounding gas reservoirs, lighting them up like a neon sign. This could have happened as recently as a few million years ago, a blink in cosmic time. The haze, in this view, is not ancient exhaust, but the still glowing aftermath of the black hole's last major tantrum. This signal is a perfect example of a cosmic message we can detect but not yet decode. The microwave whisper is clear, a testament to relativistic particles dancing in magnetic fields within unseen gas. But the story they tell, whether one of slow accumulation or sudden catastrophe, remains a matter of intense debate, a reminder that even the quietest hum from space can point to histories of unimaginable power. Sometimes the most profound cosmic whispers are not loud bursts, but a faint, pervasive glow. Across the Milky Way, a subtle signal permeates the spaces between the stars, a murmur in the microwave portion of the spectrum known as anomalous microwave emission. Unlike the sharp 21-centimeter line from hydrogen or the brilliant flash of an FRB, this signal is a broad, smooth hum, and it has one very peculiar trait. It is tightly correlated not with hot gas or magnetic fields, but with the densest, coldest clouds of interstellar dust. This is the signature of something small, something countless trillions of times over, doing something incredibly simple. The leading explanation is as elegant as it is strange. Imagine the space between stars filled with minuscule specks, nanoparticles of carbon or silicate smaller than a virus. These are not static motes of dust. They are constantly buffeted by the faint pressure of starlight and the occasional collision with a lone atom or molecule. This tiny input of energy sets them spinning, and spinning incredibly fast, billions of rotations per second. According to the laws of physics, any rotating molecule with an uneven distribution of electric charge will emit radiation. This is the spinning dust hypothesis. It proposes that this collective, frantic pirouette of countless nanoscale grains is what generates the anomalous microwave emission, a cosmic hum born from pure motion. The theory is compelling because it uses known physics to explain an observed signal with remarkable precision. In many dusty regions, the predicted glow from these spinning nanoparticles matches the observed microwave whisper almost perfectly. Yet, like any good mystery, there are wrinkles. In some environments, the signal is slightly too strong or too weak, or its exact frequency profile doesn't align. This leaves a tantalizing gap in our understanding. Are we missing a key ingredient in the dust recipe? Perhaps a specific type of molecule or an unknown surface property that affects how they spin? Or could there be an entirely different process at work within these dense clouds, something contributing to the glow that we have not yet conceived? The anomalous microwave emission is a reminder that the universe communicates in every possible language, even the low, resonant hum of a trillion spinning specks in the dark. These spinning nanoparticles are a gentle hum compared to the radio screams coming from a star on the edge of self-destruction. In the southern constellation of Carina, a cosmic titan named Eta Carinii wages a constant war against itself. This is not a normal star. It is a luminous blue variable, a rare hypergiant class of star so massive and unstable it verges on exploding. For centuries, astronomers have watched its violent mood swings. In the 1840s, it underwent a colossal eruption, becoming the second brightest star in the sky for years without actually going supernova. That event ejected a vast amount of stellar material, creating the homunculus nebula, a twin-lobed cloud of gas and dust that now cocoons the star. It is within this violent, expanding shell that a powerful and variable radio signal is generated. The source is a collision of unimaginable scales. Eta Carinii emits a stellar wind of charged particles so ferocious it blows with the force of a hurricane moving at millions of miles per hour. This supersonic wind slams directly into the slower-moving walls of the homunculus nebula, the fossilized gas from its past eruption. When these two torrents of matter collide, they create a shockwave of staggering energy. Electrons are accelerated to nearly the speed of light within this chaotic front, and as they spiral in the magnetic fields tangled up in the gas, they scream out across the radio spectrum. This is not a steady signal. It fluctuates with the star's own volatile heartbeat, changing as the density and speed of the stellar wind shifts. Monitoring these radio cries is like placing a stethoscope on the star's turbulent atmosphere. Every change in the signal's strength and character gives astronomers a direct read on the physics of the collision zone, helping them map the invisible structure of the nebula and measure the incredible power of the star's wind. Yet for all this insight, the central mystery remains stubbornly intact. We can observe the aftermath and study the ongoing battle, but we still do not know what precise mechanism triggers the titanic eruptions like the one in the 1840s. What internal instability causes a star to violently shed its own outer layers without completely destroying itself? The radio signals from Eta Carinii are a brilliant diagnostic tool, but they are also a reminder that we are witnessing the prolonged and poorly understood death throes of a stellar monster. Eta Carinii's radio screams are born from violence on a stellar scale, but some of the universe's most precise whispers come from a far more delicate natural technology. Deep within the cold, dense clouds where stars are born, and in the swollen atmospheres of dying giants, nature has built its own version of a laser. These are astrophysical masers, natural amplifiers that take a faint microwave signal and boost it to an intense, coherent beam. The word maser stands for microwave amplification by stimulated emission of radiation. It works through a process called population inversion, where more molecules in a gas cloud are excited to a high-energy state than are in a low-energy one. When a passing photon of the right frequency triggers them, they all release identical photons in a cascade, creating a powerful, narrowband signal. It is a natural lighthouse, but one broadcasting on a single, pure frequency. The most common cosmic masers use molecules like water vapor or hydroxyl, and they often flare up in the turbulent gas around newborn stars. Their intense, pinpoint glow allows astronomers to map structures and motions with incredible precision, tracing the swirling disks and powerful jets of stellar nurseries across vast distances. But some masers are profoundly mysterious. Consider the masers from silicon monoxide, known as SiO, found in the extended envelopes of red giant stars. These signals show bizarre and unexpected behavior. They flare and fade erratically, and their structure is far more complex than our models predict. The exact chain of events or pumping mechanism that creates the population inversion in the cold vacuum of space is incredibly intricate. It might involve collisions between molecules, the absorption of specific infrared light from the star, or even chemical reactions on the surface of dust grains. We see the brilliant result, the intense signal, but replicating the exact natural recipe in our simulations often falls short. These masers are more than just tools. They are diagnostics of environments we cannot otherwise probe. By studying their polarization, how the light waves are oriented, astronomers can even map the magnetic fields threading these distant gas clouds at a resolution finer than our solar system. Each erratic pulse from a silicon monoxide maser is a direct telegram from the complex, chaotic physics occurring in the outer atmosphere of a dying star, a reminder that even nature's most precise amplifiers are governed by rules we are still struggling to read. The precise whispers of cosmic masers depend entirely on the gas they amplify. But what happens when a cloud of gas and dust refuses to speak at all? Against the brilliant backdrop of the Milky Way in the Southern Cross lies a profound patch of nothingness, the Coalsack Nebula. To the naked eye, it is a stark black silhouette, an ink blot on the starry sky, because it is a dark nebula, a cold, dense cloud of gas and dust so thick it completely blocks the light from the stars behind it. When astronomers turned their radio telescopes toward this cosmic shadow, expecting to hear the faint molecular murmurs common to all such clouds, they were met with a startling quiet. The Coalsack is not just dark to our eyes, it is strangely silent to our instruments. It lacks the expected chorus of certain molecular line emissions, the specific radio frequencies that molecules like carbon monoxide naturally sing out. Even the faint, pervasive crackle of synchrotron radiation, the background hum from cosmic rays, seems suppressed within its borders. This is a mystery of absence, a negative signal that challenges everything we think we know about interstellar chemistry. Why is this cloud so quiet? One possibility is its sheer, suffocating density. The internal structure of the Coalsack may be so compact and cold that the processes which normally excite molecules and cause them to emit radio waves are effectively frozen shut. The molecules are there, but they are in a state of deep hibernation. Another clue may lie in the dust itself. Perhaps the composition of the dust grains in the Coalsack is fundamentally different, coated with thick layers of ice that lock away key chemical ingredients or prevent the formation of the complex molecules that typically produce these radio lines. This silent sentinel forces us to reconsider our models. We build our understanding of the universe on the signals we can detect, but the Coalsack teaches a crucial lesson. Sometimes the most important message is the one that isn't there. Its radio silence is not an empty void, but a data point written in absence, telling us that the journey from cold, dark cloud to stellar nursery may have a silent, mysterious phase we are only beginning to perceive. The profound silence of the Coalsack Nebula is a local mystery, but it pales before a cosmic emptiness of staggering scale. Far beyond our galaxy, in the constellation of Boötes, lies a region of space so vast and desolate it defies comprehension. The Boötes void is a spherical chasm in the universe roughly 330 million light-years across. If you placed the Milky Way at its center, the nearest edge of this void would be over 150 million light-years away. In a volume of space that should contain thousands of galaxies, astronomers have found only a few dozen. It is a cosmic desert on a scale that challenges our understanding of how matter clumped together after the Big Bang. Yet, even in this immense nothingness, there is a whisper. Radio telescopes have detected the faint, telltale signature of the 21-centimeter line from neutral hydrogen within the void. This signal implies the presence of a few isolated clouds of primordial gas drifting through the abyss. Their detection is a monumental puzzle. How did these fragile clouds of hydrogen survive in a region where the gravitational pull of galaxies should have either drawn them in or torn them apart eons ago? Their faint emission suggests they are not associated with any visible stars. They are dark, lonely ghosts in the cosmic machine. One compelling theory is that these are dark galaxies, failed attempts at cosmic construction. Imagine a cloud of gas with enough mass to potentially form a galaxy, but lacking the necessary density or trigger to ignite star formation. It would remain a silent, invisible reservoir of hydrogen, detectable only by its faint radio hum. Another possibility is that they are the last gaseous remnants of a galaxy that was long ago stripped bare by gravitational tides, its stars scattered into the void, leaving only this wispy shroud behind. The most tantalizing idea is that these clouds are truly primordial, pristine packets of gas that have existed since the dawn of the universe and, through sheer chance, never felt the gravitational tug to collapse and form stars. They would be cosmic fossils, preserving the chemical state of the early universe in a perfect, sterile deep freeze. The whispers from the Boötes void do more than just report on a few clouds of gas. They challenge the very models of how the universe's large-scale structure, the great cosmic web of filaments and voids, formed and evolved. Their existence suggests that even the emptiest places in the cosmos may hold secrets, silent and ancient, waiting for the right instrument to hear their story. The profound emptiness of the Boötes void highlights a universe of extremes, but our own galactic neighborhood holds a river of gas so immense it wraps around the entire sky. Stretching for over 600,000 light-years, a faint, ethereal ribbon of hydrogen drifts through the darkness, connecting two of our closest galactic companions to the Milky Way. This is the Magellanic Stream, a cosmic river of gas torn from the large and small Magellanic Clouds as they dance around our galaxy. Its presence is betrayed by the gentle, universal hum of the 21-centimeter line, a clear radio echo that maps its serpentine path across the heavens. But this signal is not a simple whisper, it is a complex story written in static. The detailed profile of its radio emission reveals a deep puzzle. The hydrogen signal is clear, yet its structure is frayed, and its ionization levels are unexpectedly high, meaning many of its hydrogen atoms have been stripped of their electrons. This suggests a violent and complex history, a journey through a hostile environment. The stream is not drifting through a perfect vacuum. It is plowing through the Milky Way's own extended halo, a diffuse and hot corona of gas that envelops our entire galaxy. This interaction, combined with the intense ultraviolet radiation blasting from the stars in our galactic disk, is slowly cooking and tearing the stream apart, ionizing its atoms and sculpting its frayed edges. The central debate among astronomers is not about its existence but its birth. Was this colossal river of gas pulled out primarily by tidal forces, the sheer gravitational tug of war as the Magellanic Clouds swing past the Milky Way? Or was it ram pressure stripping where the clouds, moving at high speed, slammed into the thin gas of our galactic halo, having their own gas scoured away like leaves in a hurricane? The stream's faint, diffuse radio signature is more than just a map of lost gas, it is a probe. By studying how its signal is altered, astronomers can use the Magellanic Stream as a diagnostic tool to measure the invisible properties of our galaxy's own hidden corona, its density, temperature, and extent. This ghostly river, visible only by its radio echo, is both a casualty of a galactic interaction and a brilliant natural instrument, revealing the contours of the invisible ocean our galaxy swims within. The faint radio whispers from the Magellanic Stream map a river of simple atoms, but other cosmic clouds broadcast in a far more complex chemical language. Switch your perspective from radio waves to the infrared, and a stunning new layer of the interstellar symphony reveals itself. Across countless nebulae and star-forming regions, astronomers detect a series of broad, unidentified infrared bands. These are not the sharp, precise lines of single atoms, but broad, smeared-out hums like the blurred notes of a massive choir. They are the spectral fingerprints of something large and intricate, and the prime suspects are complex organic molecules known as polycyclic aromatic hydrocarbons. Imagine the soot from a candle flame, tiny flakes made of rings of carbon atoms fused together in honeycomb patterns. These PAHs are thought to be abundant throughout space, and when they are warmed by starlight, they vibrate and emit these distinctive infrared bands. Their signal is a profound revelation. It tells us that the basic building blocks of life, complex carbon-based chemistry, are not rare on Earth alone. They are forged in the furnaces of dying stars and scattered liberally across interstellar gas clouds, becoming part of the raw material for new solar systems. This is a cornerstone for astrobiology, evidence that the universe is pre-loaded with organic ingredients. Yet for all their importance, these bands hold a stubborn mystery. No single molecule we know from Earth, no specific type of PAH, matches all the observed bands perfectly. The infrared signature we see is a composite, a crowd-sourced hum from a vast family of related molecules, each with slightly different structures. Even more puzzling is their resilience. These complex molecules are detected not just in the sheltered cocoons of dense clouds, but out in the harsh, diffuse interstellar medium, bathed in brutal ultraviolet radiation that should tear them apart. How do they survive? One theory suggests they are protected by clinging to the surfaces of dust grains like moss on a rock, shielded from the full fury of the starlight. Another posits they exist in a constant cycle of destruction and reformation, getting shattered by photons only to rapidly reassemble in the cold vacuum of space. The unidentified infrared bands are a triumphant and frustrating signal. They confirm that organic chemistry is a universal process, but they also remind us that the specific recipes cooking in the cosmic clouds are more diverse and mysterious than our current catalog can name. The infrared bands from complex molecules are a chemical signature we can see, but the most stubborn spectral mystery in astronomy is written in darkness. For over a century, astronomers have studied the light from distant stars and noticed something peculiar. Superimposed on the rainbow of starlight are hundreds of faint, dark lines where specific colors are missing, absorbed on their journey to Earth. These are the diffuse interstellar bands, and they do not come from the stars themselves. They are imprinted by the diffuse clouds of gas and dust that the starlight passes through. The first of these dark lines was spotted in 1922, and since then we have catalogued well over 500 of them. Each one is a barcode stripe from a specific, unknown molecule floating in the vast emptiness between the stars. Think of it like this: you are listening to a pure musical note from a faraway instrument, but by the time it reaches your ears, hundreds of specific, tiny frequencies have been subtly muted. The muting agent is out there in the dark, and we still do not know what it is. The hunt for the culprit has become one of the great chemical detective stories in science. Early suspects were simple carbon chains, long strings of carbon atoms that could absorb light in predictable ways. A major breakthrough came with the confirmed detection of Buckminster fullerene, the soccer ball-shaped C60 molecule in space. Its ionized form, C60+, was finally matched to several of the diffuse interstellar bands after decades of searching, a triumphant solve for a handful of the lines. But that victory highlighted the scale of the problem. It explained maybe 5 bands out of more than 500. the rest remains stubbornly unidentified. The current thinking points toward even larger and more complex organic molecules, perhaps similar to the polycyclic aromatic hydrocarbons but in different charged states or wrapped around other atoms. The profound challenge is that these molecules are in a state we struggle to recreate on Earth. They are isolated, cold, and bathed in subtle interstellar radiation fields. Reproducing their exact absorption signature in a laboratory is incredibly difficult, like trying to copy the exact sound of a violin played in a cathedral by testing the instrument in a silent, padded room. Yet, for all the mystery, these dark lines are incredibly useful, because each unknown molecule absorbs light at a very specific frequency. The strength and shape of a diffuse interstellar band tells astronomers about the conditions inside the cloud it comes from. They can trace the cloud's density, temperature, and how much radiation is pounding into it, so we use these fingerprints constantly, even though we do not know whose fingers made them. This is the essence of the mystery. We have a powerful tool born from our ignorance. These century-old spectral ghosts are a humbling reminder that the interstellar medium, the thin soup between the stars, is filled with a chemical diversity we have only begun to catalogue, its complexity written in shadows across the light of every star we see. The dark spectral lines are a chemical mystery written in missing light, but some of the most powerful signals from gas clouds are written in pure, invisible energy. The sky glows fiercely in gamma rays, the highest energy form of light, and the Fermi Large Area Telescope has mapped this violent brilliance in exquisite detail. Among its catalogue are enigmatic sources that shine only in gamma rays. They are cosmic ghosts with no identifiable counterpart in radio waves, visible light, or even X-rays to reveal their true nature. Yet, for a subset of these phantoms, there is a tantalizing clue. Their positions align almost perfectly with vast, dark molecular clouds, immense reservoirs of cold hydrogen gas drifting through the galactic spiral arms. This coincidence is the key to a dramatic theory. These clouds are not the sources of the gamma rays, they are the screens. They are nature's own particle detectors, revealing violence happening somewhere else entirely. The process begins with cosmic rays, primarily protons, accelerated to nearly the speed of light by some distant and hidden powerhouse, perhaps a supernova remnant or a microquasar. These protons travel across the galaxy until they collide by chance with the dense gas of a molecular cloud. When a high-energy proton smashes into a proton within the cloud's hydrogen, the result is a shower of subatomic debris, including particles called pions. These pions are unstable and decay almost instantly into pairs of gamma rays. The cloud itself lights up, broadcasting the violence of a collision we cannot see directly. This explains why we see the brilliant gamma ray glow but no other signal from the cloud. The cloud is cold and dark, doing nothing on its own. It is merely the canvas upon which a distant cosmic ray accelerator paints its signature. The profound mystery, then, is not the glow itself but its origin. Where is the hidden particle gun? The cosmic rays that create these gamma rays must have traveled a significant distance, meaning their source could be hundreds of light years away from the cloud we see shining. Astronomers are left to trace back the possible paths of these invisible particles, searching the empty space around the glowing cloud for any hint of a supernova shockwave or a jet from a black hole that could have launched the assault. These dark gamma ray sources turn our understanding inside out. We are not looking at the engine, but at its shadow, a brilliant afterimage of a catastrophic event painted onto a passive cloud of gas. The universe, it seems, can use its own interstellar material as a projection screen, revealing forces of incredible power that otherwise remain completely hidden in the dark. Gamma rays reveal hidden violence by painting onto passive clouds, but other signals are the ghosts of the violence itself. In the constellation of sextants, a radio telescope project called GLEAM, the Galactic and Extragalactic All-Sky MWA survey captured something truly bizarre. Designated gleam J0917-0012, it appears as an almost perfect faint circle of radio emission, a cosmic smoke ring hanging in the void. This object is a prime example of a new class called odd radio circles, or ORCs, and it presents a riddle written in polarized light. Its radio waves are not just a glow, they are aligned, a sign of strong, organized magnetic fields tracing its circular edge. The most startling fact is its scale. This ring is enormous, spanning nearly 1 million light-years in diameter, wide enough to swallow several Milky Ways side by side. It seems to be centered on a distant cluster of galaxies, a hint that its origin is tied to the most massive structures in the universe. The leading theory is that we are seeing the aftermath of a catastrophe of galactic proportions. When two galaxy clusters, each containing hundreds of galaxies and vast oceans of hot gas, collide and merge, they unleash a tsunami of energy. This merger can send a titanic spherical shockwave propagating outwards through the thin intracluster medium, the superheated gas that fills the space between the galaxies. As this shockwave expands, it could accelerate electrons and amplify magnetic fields along its leading edge, creating the very ring of polarized radio emission we observe. It would be a fossilized sound wave from a collision heard across the cosmos. A competing idea is even more mind-bending. What if we are looking straight down the barrel of a relativistic jet from a supermassive black hole? In this scenario, the active black hole at the heart of a galaxy fired two opposing jets of plasma at near light speed. If one of those jets is pointed almost directly at us, its effects would appear foreshortened, and the jet's terminal point, where it plows into the intergalactic gas and spreads out, might look like a circular lobe. We would be seeing a single, colossal bubble inflated by a black hole's outburst, viewed end-on. The signal from gleam J0917 is a ghostly imprint on the thin, hot gas between galaxies. It is not an object but an event, a temporary disturbance frozen in time by our telescopes. Whether it is the echo of colliding clusters or the headlight beam of a monstrous jet, its perfect circular form is a cosmic signature, a message from the most energetic environments in existence, written in the language of magnetic fields and fast-moving electrons. The ghostly rings of intergalactic space show us the aftermath of cosmic violence, but a much closer and quieter mystery is brewing at the very heart of our own galaxy. Just 26,000 light-years away, a silent giant is waiting. Astronomers call it G0.253 plus 0.016, but they have given it a far more evocative nickname, the Brick. This is not a diffuse haze or a thin stream. It is a colossal, dark molecular cloud, a fortress of cold gas and dust so dense it blocks all background light. In radio and submillimeter wavelengths, it appears as a massive, opaque rectangle silhouetted against the glowing center of the Milky Way. Its signals tell us it is packed with enough raw material to form over 100,000 suns like our own. By all rights, this should be a stellar fireworks factory, a frenetic nursery where gravity is crushing that gas into new stars at a furious rate. Yet, when astronomers point infrared telescopes at it, expecting to see the warm glow of countless protostars lighting up within, they are met with a profound and puzzling silence. The Brick is dormant. It is a loaded gun that refuses to fire. This inactivity is the central mystery. Why is this immense reservoir of potential, sitting in the turbulent, high-pressure environment of the galactic center, not doing what it is supposed to do? One compelling theory points to invisible architecture holding it up. The galactic center is laced with powerful magnetic fields, and the Brick may be threaded with these lines of force. Imagine the cloud's gas is like iron filings, and the magnetic field is like a strong grid running through it. That magnetic pressure could be providing a supporting structure, a cosmic scaffolding that counteracts the inward pull of gravity, preventing the cloud from fragmenting and collapsing into stars. Another possibility is sheer turbulence. The gas inside the brick may be churning with such violent internal motions, stirred by the chaotic environment of the galactic core, that it stays puffed up. It is like trying to compress a cloud of frantic bees. The constant, random motion keeps the particles from settling into a dense, star-forming pile. The most tantalizing idea is that we are simply catching the brick at a special moment in time. Perhaps it is not stable at all, but is actually on the very brink of catastrophic collapse. In this view, it is a cosmic pressure cooker that has not yet reached its tipping point. The radio signals we detect show its mass and density are extreme, but they hide the secret timing of its inevitable implosion. The brick's silence is a deep cosmic question mark. It forces us to ask what truly triggers the birth of stars. Is it simply having enough mass in one place, or is there a final, subtle switch that must be flipped, a moment of quiet before the storm that we are witnessing in real time? The brick's dormancy is a mystery of potential unrealized, but other stellar newborns announce their arrival with brilliant, chaotic radio screams. Scattered across the galaxy are tiny, intense knots of light known as ultra-compact H2 regions. The H2 stands for ionized hydrogen, gas so hot that its electrons have been stripped away, and it glows fiercely in radio waves. These regions are the immediate aftermath of a massive star's violent birth, the blistering bubbles of plasma carved out by the star's fierce ultraviolet radiation. They should be simple, predictable halos, but their radio signals tell a far stranger story. Instead of neat, spherical shells, they appear as twisted rings, irregular blobs, or even cometary shapes with long tails, all flickering and changing on timescales of just years or decades. Even more puzzling, some of these brilliant radio sources are found drifting in isolation, far from the dense, sprawling clouds where massive stars are supposed to form. How did a stellar powerhouse end up alone in the galactic darkness, and what is causing its radio cradle to morph so rapidly? One compelling theory involves a dramatic escape. Imagine a massive star born in a crowded cluster, but given a powerful gravitational kick from a nearby supernova or a close encounter with another star. This runaway star would rocket away from its birthplace at tremendous speed, still pouring out its intense radiation. If it then plows into a small, isolated cloud of gas in its path, it would instantly ionize that gas, creating a temporary, ultra-compact H2 region that flickers and distorts as the star moves through it and the cloud erodes. The bizarre shape and rapid changes are a snapshot of this violent interaction. Another idea points to a special, fleeting moment in a star's life. Perhaps these signals come from a massive star still in the final stages of accreting material from its surrounding disk. In this turbulent phase, the star's radiation and powerful winds battle against infalling gas, creating a small, chaotic zone of ionization that changes shape daily as the battle ebbs and flows. These ultra-compact regions are like the first cries of a stellar infant, brilliant and raw. Their unpredictable radio signals are direct probes into the most extreme and dynamic moments of a star's youth, a phase so violent and brief we are lucky to catch it at all. Yet their sheer variety and odd locations force us to admit that the story of how a massive star settles into its life is far messier and far more interesting than our tidy textbooks once suggested. The bizarre shapes of stellar cradles show us the chaos of birth, but the true mystery of creation begins in the deepest quiet. Before a star ignites, there exists a state of profound stillness, a cold, dense knot within a larger gas cloud known as a prestellar core. These are the cosmic eggs, the final form of raw material before gravity's final victory. Astronomers probe these dark wombs using the spectral lines of rare molecules like diazonilium or N2H+, which serve as delicate tracers of the gas's density and motion. Yet, in the very heart of these cores, where collapse should be imminent, these molecular whispers do something strange. They fade away. The spectral lines weaken dramatically or even vanish entirely right at the center. This signal of absence is not a failure of observation. It is a crucial clue written in silence. The explanation lies in a process called freeze-out. As the core grows denser and colder, approaching just 10 degrees above absolute zero, gaseous molecules like carbon monoxide and eventually even N2H+ stop bouncing freely. Instead, they strike the surfaces of microscopic dust grains drifting in the cloud and stick, forming thick, icy mantles. The molecules are still there, but they are locked in a frozen prison, unable to emit their characteristic radio line. This freeze-out is a critical switch in the star formation process. By removing molecules from the gas, it changes the core's chemistry and its ability to cool itself, directly influencing when and how the final gravitational collapse will begin. The complexity, however, is immense. The exact point at which a line vanishes depends on a delicate balance of temperature, density, and the intricate chemistry on the grain surfaces themselves. How thick do the ice mantles grow? Which molecules freeze first? These are questions we cannot answer from a simple snapshot. Observing this vanishing act is like watching a room slowly darken, but not knowing if someone is turning down a dimmer switch or simply piling more and more black velvet over the lamps. Each prestellar core is a unique experiment in deep space cryogenics, and its silent center holds the frozen recipe for a future sun. These frozen centers of prestellar cores are the quietest places in a galaxy, but the universe's largest structures roar with a silence of their own. Stretching across an almost unimaginable 10 billion light-years, the Hercules Corona Borealis Great Wall is not a wall of stone, but a filament, a vast, thread-like congregation of galaxy clusters. It is the largest single structure we have ever identified, a cosmic continent so immense it challenges the fundamental principle that the universe should look roughly the same in every direction on the largest scales. If such a titanic assembly of matter exists, it must have left an imprint on the space around it, a ghostly signature pressed into the thin gas that fills the voids between the galaxies. The hunt for this signal is not for a bright flash or a specific frequency, but for a whisper written in statistics, a subtle pattern of unevenness across the sky. Astronomers search for it in two primary ways. The first is by scrutinizing the cosmic microwave background, the afterglow of the Big Bang. As this ancient light traveled for over 13 billion years to reach us, it passed through the gravitational wells of all the structures that formed later, including the vast filaments of the cosmic web. The immense mass of the Great Wall should have ever so slightly warmed the photons that passed through it, leaving a faint, cold spot or a specific pattern of polarization in the microwave background, a cosmic shadow of the structure. The second method involves mapping the distribution of neutral hydrogen across the universe using its 21-centimeter line. By looking at the collective radio hum from hydrogen clouds at a specific, ancient distance, scientists can create a three-dimensional map of where matter was concentrated in the early universe. The signal of the Great Wall would appear as a statistically significant overdensity, a vast, faint ridge in the data showing that hydrogen clouds, and by extension, the galaxies they would form, are not scattered randomly, but are aligned along this incomprehensible spine. Detecting this imprint is a monumental challenge. It requires separating this one specific pattern from the cacophony of other fluctuations, both primordial and caused by nearer structures. It is like trying to hear the echo of a single, distant avalanche by listening to the sound of the entire ocean, yet finding it would be a direct link back to the seeds of all structure. The Great Wall's imprint would be a fossilized whisper from the universe's infancy, a barely perceptible ripple that grew over billions of years into the backbone of a continent of galaxies. Its detection would confirm that the largest patterns we see in the galaxies today were written faintly and indelibly into the fabric of the cosmos at the very beginning. These vast cosmic walls are the universe's final structure, but some of its most vital signals come from the tiniest, most energetic galactic engines. Citizen scientists scanning through images from the Sloan Digital Sky Survey first spotted them tiny, round, and glowing with an unusual emerald hue. They called them green pea galaxies, a playful name for a profoundly violent class of objects. These are not majestic spirals like our Milky Way. They are compact dwarfs, no larger than 1/10 of our galaxy's size, yet they are cosmic pressure cookers, forging new stars at a rate hundreds of times faster than our own. Their brilliant green color in the survey images is not from stars, but from a telltale signal in their optical spectra, an overwhelming glow of doubly ionized oxygen. This is the signature of gas that has been utterly blasted by an intense flood of ultraviolet radiation from countless newborn, massive stars. The gas clouds within these galaxies are not just hot, they are being torn apart, their atoms stripped of electrons in a continuous, ferocious storm. But the most crucial signal from the green peas is not in visible light. It is in the far ultraviolet, a specific emission line known as Lyman alpha. This line is produced when an electron falls into place around a hydrogen atom, and it is typically trapped inside galaxies. The dense clouds of neutral hydrogen gas that surround most star-forming regions absorb this Lyman alpha radiation and re-scatter it in random directions, effectively imprisoning the signal. In green pea galaxies, however, something extraordinary happens. The Lyman alpha line does not just escape, it escapes with a specific and unusual profile, a shape that suggests it is leaking out with surprising ease. The gas clouds in these frenzied dwarfs are not the impenetrable fortresses seen elsewhere. They are porous, riddled with holes and channels carved by powerful stellar winds and supernova explosions. This leakiness is a monumental clue to one of the universe's greatest transformations, the epoch of reionization. After the Big Bang, the cosmos cooled into a fog of neutral hydrogen. The first stars and galaxies had to burn through this fog, their intense radiation reionizing the gas, making the universe transparent to light like our own. Green pea galaxies, with their compact violence and leaky gas, are our best local analogues to those first pioneering galaxies. They show us a possible mechanism for how ultraviolet radiation could have broken free to clear the cosmic fog. Yet the precise physics remains a vibrant mystery. How exactly do stellar feedback and galaxy-scale outflows sculpt these escape routes? Why do some green peas leak radiation so efficiently while other, similarly violent galaxies do not? Each tiny green dot is a laboratory, a window back to the universe's adolescence, demonstrating how the most frantic stellar birth can punch holes in the very clouds that gave it life, flooding the cosmos with the light that defines its transparency. The violent, leaky nurseries of green pea galaxies show how stars can reshape their own homes, but the most cataclysmic reshaping of all lies in the heart of a distant cluster of galaxies. In the constellation Ophiuchus, a seemingly quiet cluster of galaxies hides a scar of almost incomprehensible violence. Astronomers studying X-ray data from the Chandra Observatory first noticed something bizarre, a gigantic, curved edge in the superheated gas that fills the cluster. It was the boundary of a cavity, a cosmic crater so vast it could contain 15 Milky Way galaxies lined up in a row. This was no gentle bubble, it was the imprint of an explosion, the Ophiuchus supercluster eruption, the single most energetic release of power detected in the universe since the Big Bang. The energy involved is beyond human scale, equivalent to detonating 20 billion megatons of TNT. The signal that reveals this cataclysm is not a brilliant flash, but a faint, diffuse whisper of radio waves, tracing the relic shockwave that still ripples through the cluster's gas billions of years after the initial blast. This radio glow comes from electrons, accelerated to nearly the speed of light by that ancient shock, spiraling around weak magnetic fields. It is a ghostly afterimage, the only remaining evidence of an event that tore through the fabric of the cluster itself. The central mystery is as staggering as the cavity's size. What cosmic engine could possibly generate such an unfathomable outburst? The prime suspect is the supermassive black hole at the cluster's core. But this was not a typical feeding frenzy. This was a black hole tantrum of epic, almost impossible proportions. The leading theory suggests that the black hole, perhaps after consuming a truly colossal amount of gas, fired a pair of jets so powerful and sustained that they bored through the cluster's atmosphere for millions of years, pushing the superheated gas aside to carve this monumental cavity. The energy required dwarfs anything we see from black holes in the modern universe. It forces astronomers to confront a fundamental question: are there limits to how violent a black hole's outburst can be, or did we simply catch a one-in-a-billion event, a perfect storm of accretion that may never happen again in our cosmic neighborhood? The faint radio relics are our only guide, a whisper from an era of demonic violence, asking us to reconsider what we thought was possible for the monsters that lurk in the dark hearts of galaxy clusters. The faint radio relics from the Ophiuchus eruption are whispers from the most powerful engines we can see, but the universe may be filled with a deeper silence, a ghost that writes its name in light we cannot explain. This brings us to the final and most profound unexplained signal, one that is not from the gas itself, but from what might be hiding within it, the persistent mystery of dark matter annihilation. For over a decade, our most sensitive gamma-ray telescopes have detected a strange, diffuse glow emanating from the heart of the Milky Way. It is not the sharp pinpoint of a star or the violent burst of a collision. It is an excess, a soft, pervasive fog of gamma-ray light centered on the galactic core that exceeds what known astrophysical sources can account for. This galactic center GVXS has sparked one of the most thrilling debates in modern science. Could this be the first indirect signal of dark matter, the invisible substance that makes up over 85% of the universe's mass? The theory is compelling and elegant. We know dark matter must exist from its gravitational pull on galaxies, but we have never detected a single particle of it directly. Theorists propose that dark matter could be made of weakly interacting massive particles, or WIMP. If these particles are their own antimatter counterparts, then wherever dark matter is dense enough, two particles could occasionally collide and annihilate each other in a flash of energy, producing standard particles like electrons and, crucially, gamma rays. The galactic center is the perfect hunting ground. It is thought to be surrounded by a vast, dense halo of dark matter, and within that halo, especially where it overlaps with the immense gas clouds of the central molecular zone, the annihilation rate could be high enough to produce a detectable glow. The excess gamma rays match the predicted profile from such a dark matter halo with startling precision, yet the cosmos is a place of natural mimics. A strong competing explanation points to a celestial chorus we have already met: millisecond pulsars. Thousands of these faint, rapidly spinning neutron stars could be lurking unseen in the galactic bulge, their collective gamma-ray emission blending together to create the same smooth excess glow. The debate hinges on the signal's fine details, the specific energy spectrum and spatial distribution of the gamma rays, which different teams interpret in opposing ways. The mystery deepens when we look beyond our galaxy. In the hot gas that fills massive galaxy clusters, X-ray telescopes have detected faint, unexplained emission lines at specific energies. These lines have no clear atomic origin, and some scientists have proposed they could be produced by a different type of dark matter particle, a sterile neutrino decaying within those vast intergalactic clouds. While conventional explanations involving plasma physics or sulfur ions are also in play, the dark matter interpretation lingers. This is the ultimate cosmic whisper, a signal of absence seeking to make itself known. We are listening to the interstellar and intergalactic gas, not for what it says, but for what it might reveal about the phantom moving through it. The possibility that we are already seeing the indirect signal of dark matter annihilation within these clouds remains a tantalizing, unresolved frontier, a quiet hint that the greatest secret of the cosmos may be broadcasting its presence on a frequency we are only just learning to hear. From the fleeting, brilliant scream of a fast radio burst to the century-old dark lines etched in starlight, every unexplained signal we have explored shares a profound connection to the vast clouds drifting between the stars. These are not random noises in the void. Each one is a precise message, a window into the universe's most extreme laboratories. They reveal the violent physics of magnetars, the complex chemistry of organic molecules, and the hidden architecture of magnetic fields woven through the cosmic web. They show us failed galaxies in empty voids, dormant clouds on the brink of collapse, and the ghostly afterimages of black hole eruptions that dwarf all comprehension. Together, they form a symphony of strange transmissions, a chorus of questions written in every wavelength from radio waves to gamma rays. The cosmos is far from silent. It is alive with whispers, roars, and hums, a conversation we have only just begun to overhear. So the next time you look up at a quiet, starry sky, remember the incredible noise just beyond our senses. Stay curious and wonder what the next great signal will be, and what new chapter of the universe's story it will finally allow us to read.